You settle into your seat, buckle up, and feel the low rumble as the jet engines spool up for takeoff. A perfectly normal flight, a business trip, a vacation, a visit home. But what if I told you that the invisible roar outside your window began in a collapsing dictatorship under air raid sirens and floodlights, with engineers working beside prisoners and scrap metal? In 1944, as Hitler's Third Reich was running out of fuel, materials, and time, German engineers lit the first practical turbojet engine, the Junkers Jumo 004. It powered the world's first operational jet fighter, the Me-262, a weapon born from desperation meant to turn the tide of a losing war. It failed to save the regime, but the engine itself? It escaped. Captured, copied, dissected by Americans, Soviets, French, and others. The Jumo 004 became the Rosetta Stone of the jet age, and the unlikely ancestor of the engines carrying you through the sky today. This is the story of how a desperate, dark wartime invention became the quiet, taken-for-granted engine of our connected world. Look around the cabin. Business travelers typing on laptops, parents soothing restless children, tourists clutching guidebooks, retirees finally taking that dream vacation. Everyone here shares an unspoken faith. Faith that these massive metal tubes will lift 80 tons of steel, fuel, and human beings 6 miles into the air. Faith that the engines bolted to the wings will not fail. That faith rests on decades of refinement, testing, and safety protocols. But it also rests on lessons learned in the most unlikely classroom imaginable, a desperate gamble in the closing days of World War II. The technology that makes your journey possible, that makes all modern air travel possible, has roots that would make most passengers deeply uncomfortable if they knew. To understand what made the Jumo 004 revolutionary, you first need to understand what came before it. In the early 1940s, every military aircraft in the world was powered by piston engines, the same basic principle that powered automobiles, only scaled up and refined. Propellers pulled planes through the air, but there were hard limits. Speed? Capped around 450 miles per hour, where propeller efficiency collapsed. Altitude? Above 30,000 feet, engines gasped for oxygen. Power? Adding more cylinders meant more weight, more complexity, more things to break. By 1939, engineers in Britain and Germany had independently begun pursuing a radically different idea, the turbojet. Instead of pistons and propellers, imagine a continuous explosion. Air rushes in the front, gets compressed, mixed with fuel, ignited and blasted out the back. The jet principle, elegantly simple, suck, squeeze, bang, blow. In Britain, a brilliant officer named Frank Whittle had been developing jet engines since the 1930s. His designs were promising but underfunded, stuck in development limbo. In Germany, a young physicist named Hans von Orheim was following a parallel path. In August 1939, his experimental engine powered the Heinkel HE-178 on the world's first jet-powered flight. It lasted 6 minutes. It proved the concept worked. But experimental flights and practical war machines are separated by an enormous gulf of engineering problems, material science, and manufacturing capability. That gulf was about to be crossed, not through careful peacetime research, but through the brutal pressure cooker of total war. By 1943, Germany was losing. Allied bombers darkened the skies over German cities daily. The Luftwaffe, once the terror of Europe, was being ground down by superior numbers. American and British piston fighters swarmed German airspace. Fuel refineries were ash. Factories crumbled under high explosive and incendiary bombs. Hitler's regime, facing the abyss, became obsessed with Wunderwaffen, wonder weapons, vengeance rockets, guided bombs, secret submarines, and jet aircraft. If Germany could field a fighter that flew 100 miles per hour faster than anything the Allies had, maybe, just maybe, the skies could be retaken. Maybe the bombing could be stopped. Maybe there was still time. Enter Anselm Franz. Franz was the head of the turbojet development program at Junkers, one of Germany's oldest aircraft manufacturers. He and his team had been working on a jet engine design since 1939, but the project had been considered a low priority, interesting, experimental, not urgent. By 1943, it became very urgent. Franz's design was called the Jumo 004. It was an axial flow turbojet, meaning air moved straight through the engine in a linear path, compressed by a series of spinning blades on a central shaft. This was more compact and efficient than centrifugal designs, which used a radial compressor. The principle was sound. The execution, under wartime conditions, required brutal compromises. Picture Franz and his team in 1943. They were not working in gleaming laboratories with unlimited budgets. They were working in facilities that might be bombed tomorrow. Every decision was a trade-off between what was ideal and what was possible. The turbine blades inside a jet engine spin at thousands of revolutions per minute. The temperature inside the combustion chamber exceeds 1,800 degrees Fahrenheit. At those speeds and temperatures, inferior materials simply disintegrate. Franz knew this. He had studied metallurgy. He understood exactly what materials he needed. He also knew he could not get them. High-temperature alloys, nickel-chromium superalloys that could withstand the inferno inside a jet turbine, were in desperately short supply. Germany's supply chains were shattered, so Franz's engineers used cheaper, lower-quality steels. The result? An engine with a service life of about 10 to 25 hours before it needed replacement or major overhaul. Some engines failed after less than 10 hours. By modern standards, this is catastrophic. A contemporary jet engine runs for tens of thousands of hours. But Franz made a cold calculation. If an engine could last long enough for a few combat missions, it was good enough. The plane might be shot down before the engine failed anyway. This was engineering at the edge of catastrophe. Remarkable ingenuity shackled to impossible constraints. And yet, it worked. Think about what this means. Franz and his team invented a way to build a functional jet engine without the proper materials. They redesigned components to compensate for known weaknesses. They accepted a lifespan measured in hours instead of years. It was like building a Formula One race car out of spare bicycle parts. Absurd, desperate, and yet somehow successful. By early 1944, the Jumo 004 was ready for production. It was mated to the most advanced airframe Germany had, the Messerschmitt Me-262. The first time an Allied pilot saw an Me-262 in combat, it must have felt like encountering an alien spacecraft. The Me-262 was sleek, shark-like, with engines slung under swept wings. When the Jumo 004 spooled up, they emitted a high-pitched whine and a plume of smoke and flame. Then the aircraft simply vanished, rocketing away at over 540 miles per hour, faster than any Allied piston fighter could dream of matching. American P-51 Mustangs, the finest piston fighters of the war, topped out around 440 miles per hour. British Spitfires were even slower. In terms of pure speed and climb rate, the Me-262 was untouchable in the air. Allied bomber crews, already enduring horrific losses over Germany, now reported a new nightmare. Fighters that appeared out of nowhere, slashed through formations with cannons blazing, and disappeared before escorts could react. German test pilots were awed. One described the sensation of flying the Me-262 as like being pushed by an angel. But the angel had fragile wings. One American bomber gunner, interviewed after the war, described his first encounter with an Me-262. His B-17 was part of a formation heading to a target deep inside Germany. Suddenly, someone shouted over the intercom. A shape, moving impossibly fast. No propeller blur, just speed. The gunner tried to track it with his turret. By the time he squeezed the trigger, the jet was already gone. Then it came back from a different angle, cannons firing. 2 bombers in the formation went down in seconds. Then, just as quickly as it appeared, the Me-262 was gone, a dot on the horizon, untouchable. The gunner said he felt something he had never felt before in combat: helplessness. Against conventional fighters, he had a chance. Against the Me-262, he had none. But the Jumo 004 was a marvel, but it was also a minefield of problems. Throttle response was sluggish. If a pilot tried to advance the throttle too quickly, the engine could flame out or suffer a catastrophic compressor stall. Turbine blades, made from inferior materials, cracked and disintegrated under stress. Fuel consumption was voracious, and by 1944, Germany's fuel stocks were evaporating. Worse still, producing the engines required skilled labor and precision tooling, both in desperately short supply. To meet production quotas, the Nazi regime turned to forced labor. Concentration camp prisoners, slave laborers from occupied territories, and prisoners of war were pressed into assembly lines under brutal, deadly conditions. Many did not survive. This is the shadow that lies across every Jumo 004 ever built. It is a machine born not only of engineering genius, but of atrocity. Even if the engines had been perfect, the Me-262 faced an impossible strategic situation. Hitler himself interfered disastrously with deployment. In 1943, he insisted the Me-262 be developed as a fast bomber, not a fighter. Precious months were wasted trying to hang bombs under an airframe designed for speed and agility. By the time the Me-262 entered combat in mid-1944, Germany's infrastructure was collapsing. Airfields were cratered, fuel trucks didn't arrive, spare parts were non-existent, trained pilots were killed faster than they could be replaced, and the Me-262, for all its speed, was vulnerable. It was slow and fragile during takeoff and landing. Allied pilots learnt to loiter near German jet bases and pounce when the Me-262s were at their most defenseless. One Me-262 pilot, captured by American forces, described the absurdity of his situation. He flew the most advanced aircraft in the world, but he had fuel for maybe one sortie per day. His airfield was under constant attack. Half his squadron's jets sat broken on the runway, waiting for parts that would never arrive. He said it felt like commanding a Ferrari in a junkyard. Technically superior, strategically meaningless. Could the Me-262 have changed the war? It's a question that haunts historical analysis. Some estimates suggest that if the Me-262 had been deployed earlier and in larger numbers, say in 1943 instead of late 1944, it might have inflicted significantly heavier losses on Allied bombers. But heavier losses does not mean victory. By 1944, the Allies had overwhelming industrial and numerical superiority. Germany was being crushed from the east by the Soviets and from the west by American and British forces. Even if every Allied bomber over Germany had been shot down, it would not have stopped the Red Army or the D-Day invasion. At best, more effective Me-262 deployments might have prolonged the war by months, at the cost of tens of thousands more lives. At worst, it could have encouraged the Nazi leadership to continue a hopeless fight even longer, multiplying suffering. It is sobering to realize the Me-262's failure to appear in time may have been a mercy. By the spring of 1945, the Third Reich was dying. Allied armies swept across Germany from east and west. Factories were captured. Test facilities were overrun. Engineers and scientists were rounded up, some arrested, others recruited by the victors. The Me-262 production lines fell silent, but the engines did not disappear. Imagine an American intelligence officer walking into a captured factory in April 1945. The building is half destroyed, scarred by bombing. Inside, rows of Jumo 004 engines sit on assembly stands, some complete, some half-finished. He picks up a technical manual, written in German, flips through pages of diagrams and specifications. He doesn't understand all of it, but he understands enough. This is treasure. This is a shortcut past years of research and development. This is the future, sitting in a bombed-out factory in the ruins of the Third Reich. He radios his superiors. Within days, crates are being loaded onto transport planes. The same scene played out across Germany, repeated by Soviet officers, British engineers, French teams. Everyone wanted the jets, everyone wanted the engines, everyone understood what they represented. American, Soviet, British and French intelligence teams raced across occupied Germany, hunting for technology. They found warehouses full of Jumo 004s. They found blueprints, test data and prototypes. They found engineers willing or forced to talk. The Nazi regime collapsed into ash and rubble. But the Jumo 004, the desperate gamble of a dying dictatorship, was about to begin its second life. In the chaos of 1945, the victorious Allies launched one of history's greatest technology heists. It wasn't espionage in the traditional sense. It was closer to an enormous, multinational garage sale, except nothing was for sale, everything was simply taken. The Americans launched Operation Paperclip, quietly relocating German scientists and engineers to the United States, along with crates of equipment and documents. The Soviets dismantled entire factories, loaded them onto trains, and shipped them east. The British and French grabbed what they could. At the center of this scramble were the German jet engines, especially the Jumo 004 and its smaller sibling, the BMW 003. Why? Because these were not laboratory curiosities. These were engines that had actually flown, actually fought, actually worked under combat conditions. They represented a fully realized proof of concept, with thousands of hours of test data and operational experience baked in. For Allied engineers who had been struggling with their own jet programs, the Jumo 004 was a Rosetta Stone, a working translation of abstract theory into metal and fire. The Soviet Union wasted no time. Engineers dismantled captured Jumo 004s and reverse-engineered them down to the rivet. The result was the RD-10, a near-identical copy, which powered early Soviet jet fighters like the Yakovlev Yak-15. Later, Soviet designers used the Jumo 004 as a foundation to develop more advanced engines. The lessons learned about axial flow compression, combustion chamber design, turbine blade cooling, became the bedrock of Soviet jet propulsion for decades. It is no exaggeration to say that the Soviet Union's Cold War jet fleet owed a direct debt to Anselm Franz's wartime designs. Here's the remarkable thing. By 1946, former enemies were all studying the same engine. American engineers in Ohio, Soviet engineers in Moscow, French teams in Paris, British specialists at Farnborough, all of them taking apart Jumo 004s. All of them measuring, testing, learning. The engine became a strange kind of common language. Not a political unification, but a technological one, everyone learning from the same source. Everyone leapfrogging past problems the Germans had already solved. The United States took a different approach. American companies like General Electric and Pratt & Whitney were already developing their own jet engines, some based on Frank Whittle's British designs. But the Germans were ahead in certain areas, particularly in axial flow compressors. American engineers studied the Jumo 004 intensely, not to copy it directly, but to understand its principles and refine them. The result was a generation of American jet engines, such as the General Electric J47 and the Pratt & Whitney J57, that incorporated lessons from both British and German designs. These engines would go on to power iconic American jets, the F-86 Sabre, the B-47 Stratojet, and eventually early commercial airliners. France and Czechoslovakia both produced licensed or modified versions of German jet engines. In Czechoslovakia, the Avia S-92 fighter used a copy of the Jumo 004. In France, captured German engines helped jumpstart the French aviation industry's post-war recovery. Even countries that did not directly copy the Jumo 004 studied it carefully. Britain, though ahead in some areas thanks to Whittle, absorbed German insights into materials and manufacturing. The Jumo 004 had become a universal textbook read by every nation that wanted to compete in the jet age. But the most profound transformation was still to come. In the late 1940s and 1950s, the jet engine began its migration from the military to the civilian world. The first jet airliner to enter service was the British de Havilland Comet in 1952. It used turbojet engines derived from British designs, but those designs had been informed by German research. In 1958, the Boeing 707 began transatlantic service, revolutionizing air travel. Its engines, Pratt & Whitney JT3s, were axial flow turbojets, descendants of the engineering principles proven in wartime Germany. Over the following decades, jet engines evolved into high-bypass turbofans, exponentially quieter and more efficient. But the core architecture, axial compression, annular combustion chambers, multi-stage turbines, remained recognizable. Draw a line from the Jumo 004 to a modern General Electric GE90 or Rolls-Royce Trent, and you will see a clear family resemblance. Not a direct copy, but a lineage, a genealogical thread running through 80 years of aviation history. Consider what this means for your own life. If you've ever flown across the country to see family for the holidays, that trip was possible because of lessons learned from the Jumo 004. If you've ever taken a business trip that would have required days by train or ship, but instead took hours by air, That convenience exists because engineers in the 1940s and 50s absorbed and refined the principles proven by German wartime jets. If you've ever visited another continent, walked streets you'd only seen in pictures, experienced cultures vastly different from your own, that entire experience was enabled by jet technology that traces its roots back to that desperate gamble in Nazi Germany. The engine designed to kill became the engine that connected the world. Today, every time you board a commercial flight, you are entrusting your life to a machine whose conceptual DNA includes fragments of that desperate, brutal wartime gamble. The Jumo 004, born in a collapsing dictatorship, has become the distant ancestor of the engines that carry millions of people safely across the world every single day. How did a weapon of war become an instrument of peace and connection? How did the engine of a fascist wonder weapon become the workhorse of global tourism, business, and family reunions? It is one of history's strangest, most unsettling ironies. But we cannot tell this story without confronting its moral weight. The Jumo 004 was not built in a clean laboratory by well-paid engineers working 9-to-5 shifts. It was built in factories where forced laborers worked until they collapsed. It was assembled by prisoners from concentration camps, many of whom did not survive the war. The materials that forged its turbine blades were scraped together from a continent being bled dry by totalitarian violence. Every Jumo 004 engine is, in some sense, an artifact of atrocity. So how do we reckon with this? How do we celebrate the engineering achievement without sanitizing the horror that surrounded it? How do we acknowledge that the same metal and fire that once powered a genocidal war machine now powers your flight to see your family or your vacation to a distant country? There is no easy answer, but there is a framework. Technology in itself is neutral. Physics does not care about ideology. A jet engine obeys the laws of thermodynamics, whether it is built in a democracy or a dictatorship, but the use of technology is never neutral, and the conditions under which it is created matter. The Jumo 004 was a tool of fascism, but after the war it became something else. The same principles, the same engineering insights were redirected toward peaceful purposes. This does not erase the suffering that went into its creation. It does not absolve the regime that built it. But it does illustrate a deeper truth. Human knowledge, once discovered, cannot be undiscovered. The engineers who suffered and died in those factories gave the world something, whether they intended to or not. Their labor, coerced and brutal as it was, contributed to a body of knowledge that eventually served the whole world. We owe them memory, we owe them acknowledgement, and we owe it to ourselves to use what they built for better ends than the ones it was designed for. There is also a strange, quiet justice in what happened to the Jumo 004. The regime that built it intended to use it to extend its dominance, to terrorize its enemies, to carve out a 1,000-year Reich. Instead, the regime lasted 12 years and died in flames. But the engine outlived it. The engine was captured, studied, copied, and spread across the world into the hands of former enemies, allies, and neutral powers alike. The Me-262 was meant to be a symbol of Aryan supremacy. Instead, it became a universal lesson, studied by Soviet engineers, American corporations, French designers, and British scientists. In the end, the Jumo 004 did not serve nationalism. It served knowledge. And knowledge, however darkly it is born, tends toward the universal. Consider the people who built the Jumo 004 under duress. Prisoners who tightened bolts with trembling hands. Laborers who assembled components they barely understood, under threat of violence. They are mostly forgotten now. History does not record their names, but their hands touched every one of those engines. When Soviet engineers reverse-engineered the RD-10, they were inheriting not just German engineering, but the anonymous labor of those prisoners. When American companies refined axial flow compressors, they were building on foundations laid by people who had no choice, no freedom, no future. This is uncomfortable. It should be. Progress is rarely as clean as we pretend. Today, when you sit in seat 23A and hear the engines hum to life, you are participating in a vast interconnected system of global movement. Every year, more than 4 billion people fly. Families reunite across continents. Businesses operate across time zones. Cultures intermingle. The world, for all its fractures, is stitched together by jet engines, and buried deep in the ancestry of those engines, hidden in the blueprints, the test data, the hard-won lessons about metallurgy and aerodynamics, is the ghost of the Jumo 004, a machine born in desperation, built by slaves, designed to kill. And now, transformed, domesticated, refined, it carries you gently through the sky. Think about your last flight. You probably didn't think about the engines much, except maybe during takeoff. You probably worried more about legroom or whether your carry-on would fit in the overhead bin. That casual indifference is, in its own way, a triumph. It means the technology has become so reliable, so mundane, that we take it completely for granted. But that reliability was built on hard lessons, on failures and crashes and incremental improvements, on the foundation of wartime research done under unthinkable conditions. Your safety, your comfort, your ability to cross an ocean in the time it takes to watch a few movies, all of it rests on that foundation. This is not a story with a simple moral. It is not a tale of heroes and villains, though both are present. It is not a story of inevitable progress, though progress did occur. It is a story about the strange, tangled, morally ambiguous way that history actually unfolds. It is a story about how the worst of humanity and the best of humanity can, sometimes, be woven together in the same object. It is a story about the Junkers Jumo 004, the engine that escaped the war that created it and became the unlikely foundation of the world we fly through today. Anselm Hans, the chief engineer of the Jumo 004, survived the war. He was brought to the United States under Operation Paperclip. He continued working on jet engines for decades, contributing to American aviation technology. He died in 1994, having witnessed his wartime creation evolve into something he could never have imagined in those desperate days of 1944. Did he feel pride, shame? Both? We don't know. He rarely spoke publicly about his wartime work. But his legacy is undeniable. Every modern turbofan owes something to the desperate innovations he pioneered under impossible constraints. So, the next time you board a flight, take a moment, feel the rumble as the engines spool up. Watch the ground fall away. Feel the strange, miraculous fact of flight. And remember, you are riding on the shoulders of history, brilliant and terrible, innovative and brutal, a testament to what humans can create, and a warning about the cost of creation. The jet engine began in darkness, but it carried us eventually toward the light. That transformation from weapon to wonder, from death machine to life-giver, is the hidden story humming just outside your window, 35,000 feet above the earth. How did a desperate, dark wartime invention become the quiet, taken-for-granted engine of our connected world? Now you know, and you will never hear that engine the same way again.